Off the bat, welcome to the last panel of the last day of the Rural Energy Conference. Thank you for sticking around. Just a note, please turn your cell phones to vibrate if you haven't already. Again, I mentioned we're on a truncated time scale with this session. We only have an hour and 15 versus the hour and 30 that everybody else has. We're going to try and keep things moving along pretty quickly, and we're going to leave questions till the last so we can, again, try and move things forward. If you have not filled out a evaluation form for the Rural Energy Conference, please do so before you take off, and you can leave those at the front table. We're in a little bit different order than what's in your schedule, but I'm going to introduce first George Hornberger, who for 20 years was with Iliamna Air, and for the last 6 years has been the general manager of Iliamna, Newhalen, Nondalton Electric Cooperative. And George, come on up.
Thank you, Josh. I manage INN Electric Cooperative. It's Iliamna, Newhalen, Nondalton. We're located in southwest Alaska, Iliamna Lake area. If nobody knows where that is, if you've heard of Pebble, well, we're right in the middle of Pebble country. Let's see, we got that right there. We have a run-of-the-river hydroelectric project. The top picture right there is our control building in the middle of winter. We're putting out full hydro right there. Next picture down is our intake area here. Springtime, and then in the summertime there. Run-of-the-river means there's no dam. We have no water storage. We use the water or we lose it. You can see the intake there. We pull water in at the intake, drop it 120 feet underground. This turbine room here is 120 feet underground. Go through a couple of turbines, and then put it back in the river. There's the tail race there. It goes 240 feet underground back out into the river. Our normal load is about 500 kW. You can see over here the two turbines going. And so in an attempt to maximize the hydro plant and use all the water, because if you don't lose it or use it, it just goes over the falls, we put in some electric boilers. Up here, the 150 kW electric boiler that we have in the Newhalen school. We have a couple of residential boilers, 20 and 30 kW. We also have a 100 kW boiler in the Nondalton school. And then this year, for the first time, we also put in a big interruptible service in a lodge out in Iliamna, the Rainbow King Lodge. They put in a bunch of electric heaters, electric water heaters, a huge electric commercial dryer, a walk-in freezer. I can't remember what all they put in, but they've been real happy with it. We sell that power at 12 cents a kilowatt hour. Strictly interruptible. We can turn it on and off anytime, day or night, and we do. With Rainbow King Lodge, we made a deal because they went all electric and no backup. If we have to go on diesel power for more than 48 hours, then they start paying the full diesel price. Hopefully that won't happen. Part of when you start maximizing a hydro, you got to keep it going. If you're going to make any money off of hydropower, you have to keep it going. And renewable energy isn't easy. In fact, it's a pain in the butt. And to start with, one of the things we do is clean trash screens. You can see the screens up here. In the fall time, the leaves start coming off the trees and they start clogging things up. We go up about probably every 3 or 4 days now, and we pull these screens up and hose them down with a high pressure hose and blow all the leaves and stuff back in the river. If we don't do that, it'll shut the hydro plant down, and usually it shuts it down in the middle of the night. In the wintertime then, as things start freezing up, we get frazzle ice, and this is especially vexing, I guess. I have other 4-letter words for it, but we won't go there right now. But frazzle ice is when the temperature of the water is below freezing and it starts collecting on rocks and everything. You can see the ice coming down the river here, and it clogs trash racks. And the only cure was to go up and scrape ice off, which was also a pain in the butt. But with the help of Alaska Energy Authority, we invented some heated trash racks. You can see the one on the right here is heated. The one on the left here is not heated. And so you can see the difference there. With the heated trash racks now, most of the frazzle ice just melts right through the trash racks and goes on through the turbines, and we can usually sail on through. Last winter we did have a lot of problems. The river was pumping out so much ice that the trash racks couldn't keep up with it, and so we spent a lot of time up there scraping ice and shoveling it out. Again, just if you want this power, you've got to be willing to work for it, and my workers will tell you that I'm a taskmaster. I work them really hard. And then we have ice jams. That's our intake deck there. I don't know if you remember a while back I showed you some pictures of an intake deck. There's what it looks like when it should look like it, and there's what it looks like when it's bad. And the only thing I can say is when you see something like that, you go, oh my God, what am I going to do now? This particular ice jam happened on December 23rd, a couple years ago. There was about 8 feet of ice on the intake deck. Out here, there was huge sheets of ice blocking the intake. It took a crew of guys a few days to clear that out. And then our tail race freezing closed. That's another one. This is 120 feet underground, 240 feet going back out into the river where the water dumps out. We were freezing shut and couldn't release water out of the turbines. We couldn't carry a full load because the turbines just simply couldn't release the water. And so what we did was actually roped, I think it was 4 guys down a cliff on the outside with a chainsaw, ice chisels, ice picks, and anything else we could think of. And they started beating their way in from the outside of the tail race, and then myself and another guy went inside, and you can see all the ice here that we beat down, and we opened it up. And when we got done, we started up the turbines and washed the ice out and went for it again. And then there's trash in the turbines. These 2 pictures here were taken at about 2:30 in the morning. The power went down and we went up there. We opened up that particular turbine, and one of my guys said, holy cow, looks like a beaver's building a house in here. And there was rocks. You can see, in fact, right here, there's actually a little piece of 2x6. I don't know where that came from, but somehow it got in there. And then there's rocks in the intake. One of the ice jams took out all of the trash racks, literally destroyed the trash racks, and it was like a bulldozer plowed rocks into the intake. And so with the help of Alaska Energy Authority, we invented this rock sucking machine here. And we started sucking rocks out of our intake box. There we are dumping our drum of rocks. And this is not easy work. The thing to remember when you look at these guys is you'll notice they're pretty bundled up. It was about 15 below zero when that picture was taken. It was miserable. And then we have turbine slush. This was last winter, I believe, and happened about 6 o'clock at night. We had an ice jam that cut loose and blocked our intake, and it sucked all the water out of the intake and sucked a turbine full of slush. And we finally ended up leaving that overnight, and the next day we took up as many 5-gallon buckets of hot water as we could find and dumped it in the turbine to get rid of the slush. It was packed in there incredibly tight. The thing to remember always when you're dealing with hydropower is there is a pot of gold at the end of the rainbow, and I wouldn't trade it for anything. It's a challenge, but it's worth it in the long run. But if you want it, you got to really want it. You got to work for it. Thank you.
Well ahead of schedule. Thank you. All right. So next up, we are going to have Marc Mueller-Stoffels present, and he's going to be talking about impacts of system control sophistication on maximizing or maximal renewable energy contribution. see here, where is his? Marc Mueller-Stoffels is a research assistant professor and program director for the Power Systems Integration Program at Alaska Center for Energy and Power. Marc's research focuses on the integration of variable generation sources into isolated microgrids. Most recently has led studies to increase renewable energy contribution in the Nome and Cordova grids. Marc and his team are also involved in R&D and testing of energy storage and control systems for high-penetration renewable energy diesel hybrid systems. Marc holds graduate degrees in physics from the University of Alaska Fairbanks and Otago University, New Zealand. Is that how you say that? Otago. I apologize. Welcome, Marc.
Thanks, Josh. All right. Is this forward, backward? I had a title slide. There we go. I apologize. I just came over from the lab. We're commissioning equipment today. Just before I left, we spun up a flywheel, so this might be a little rocky, but it's been a crazy week. So what I'm presenting on is a little bit of work I did together with Phil Maker of Power Water in Australia. So it's fairly, I'm mentioning a lot of PV here because we used a PV diesel hybrid system as a workhorse for the data for this, but everything I'm presenting also more or less applies to wind diesel hybrid systems. So what we've looked at is essentially what can you do theoretically? How much renewable energy can you put on a grid that is generally diesel powered and has the typical limitations of diesel power? The reason we're doing this is there are a whole lot of systems that could potentially run more optimal, and the reasons for that are quite often in the way they're controlled. I'm not saying those are the only reasons, but that can be a big one. There's a whole lot of approaches that we think maybe do not work, and Phil Maker has a whole lot more to say. He's been around the block several more times than I have on that. And as far as we know, this hasn't been formalized before. We know that there is a table that says, there's a classification of what makes a low penetration system, medium penetration system, and so on. And we just wanted to know whether that can be nailed down a little bit more. Okay, at some point I'm going to get this right. Okay. So this is a research question, and of course it's obvious why both Australia and Alaska have quite a lot of these small diesel grids or hybrid diesel grids, and actually the rest of the world has even more. And the integration with existing infrastructure often requires a whole lot of design decisions, and you either have to respect what you have or you have to plan for what you want. And that's something that's actually really interesting that comes out of this study, is that the different sizes of diesels you have in your plant actually determines quite a bit of how much the maximum penetration levels can be in your hybrid system if you go that route. And yeah, you have fixed numbers of diesels, and their sizes are fixed. Their lifetime is generally 20+ years. So you won't just be changing them out just because you're adding a renewable resource, so you have to figure out how to make that all fit. And adding too much renewable energy can be a problem. For one, it can damage the diesels by having too much ramp rates or too low a loading, depending on how you're operating your plant. You can also damage all kinds of other equipment due to power quality issues, and on top of that, potentially your reputation by having too many blackouts. And at the same time, you would then damage your bottom line. Just to brush over what we're talking about, these are very small systems. Generally, we have a diesel plant with X many diesel gensets, potentially a battery bank or not. We're not going into that. Solar or wind, and then you're delivering power to a village. And generally, we're looking here at systems between about 100 kilowatts and 2 megawatts. And that's a typical load profile for an Australian village in this case. And you can see that there's a diurnal variation in there, and then there's local, very short-term variations in the load. And that's really the interesting thing, and that tells you how much larger your diesels have to be than what the actual demand is. It's called spinning reserve. Oops. And in this case, when you look at second-by-second changes, the maximum change is around 40 kilowatts per second. Now, you want to know, how much can your load grow in about a minute. In an emergency, you can bring on a small diesel within a minute if you're keeping it in hot standby. So that tells you the diesel sizing and how conservative you have to run. Now, when you look, and this is really the problem with renewable energy, particular wind and diesel, you get massive oscillations. So what we've seen with PV in this data is losses of over 40 kilowatts a second of a 30 kilowatt array. So that means between 6 to 12 seconds you're losing 80% of your production, and somebody else has to provide that then, which is the diesel. Now forward, here we go. Okay, so this is the kind of changes you would see, sudden changes in diesel in solar output here in red, and you see that this is much more than what you'd see just in changes of load. So all of a sudden you have to keep much more spinning reserve potentially to keep your plant running without risking a blackout. Am I going to get this right? Okay. So the diesels generally provide the stability in the system. They provide the spinning reserve. And to operate them economically, you don't generally want to permanently underload them. So you have to also make sure that you don't have too much renewable energy in the system, because your diesels still have to run essentially in some form of a very lowly loaded mode. There are approaches to push the load lower on the diesels without damage, but in general we're looking at 20 to 30% loading, and that's what we used for the study here. If you oversize either your diesels or your renewable resource, and of course you're increasing your cost, and you'll have a harder time running economically. So we looked at what can be done under certain assumptions and certain control regimes. And our assumptions are that our diesels here cannot be loaded lower than 20% for any kind of longer duration, and that the renewable energy resource is sized to the load and not just oversized several 100%. So meaning if you have a village that has generally an average demand of 500 kilowatts or peak demand even, then you wouldn't go much larger than that on your renewable resource. Else you're not looking at the economics right, I think. The minimum load in the system is 30% of the peak load, meaning the load variation doesn't go from 0 to some maximum load, but there's always some demand in the system. And then we have limitations to this model. This is a rather theoretical study at this point, but it informs a few things. There's no hysteresis in the system, no minimum runtime on the diesel. So we're kind of reducing the complexity of what is diesel scheduling. We're not considering power quality issues at this point, because we're just running an energy balance model. And we're only running 1 or 2 diesel generators. Okay, so the first step, and this is what happens when you essentially have a lot of people just putting on PV behind the meter on their rooftop, is that the powerhouse doesn't necessarily know how much renewable energy is even in the system. Okay, at that point, the utility has a big problem, because if that is a significant portion of the current demand and it suddenly drops away and they don't know about it, then they potentially haven't kept enough spinning reserve, or vice versa. They have to keep much more spinning reserve just because there is renewable energy on the system they don't know about, but that could suddenly break away, you know, and just look like a massive motor start, and they have to match that with their diesels. So that can be a big issue. But nonetheless, what is up with this? I'm sorry. Where is actually the receiver for this? Because there, okay. Nonetheless, even in these kind of systems, you can actually integrate quite a bit of renewable power, but it depends a lot on what your genset size is. Now we're looking at 2 gensets, and here we're seeing that, you know, one of them should be about 40% of the total load or demand size, and the other one about 60%. And you can actually get to about 70% penetration. Now this is directly tied, you know, the top penetration level here is directly tied to the amount of spinning reserve you would want to keep in your system and the minimum optimal loading that you decide on. And then the average can be around 70% if the diesel plant is laid out that way. So that the next step would be to then at least have a signal from all these distributed PV panels or wind turbines, so the utility actually knows what is going on behind the meter or somewhere where somebody is generating renewable power, so they can plan for that and keep a different set of spinning reserve based on how much renewable energy is in the system. And actually that doesn't make a big difference, or it doesn't look like it would make a big difference. Dynamic spinning reserve schemes don't really increase the average renewable penetration that's possible. Nonetheless, and I'm sorry I don't have a graph for it, but it does increase the fuel efficiency of the system quite significantly, because you can actually run smaller diesels at higher loads in this kind of setup. Now the next step up would be to have control over your renewable resources and to be able to curtail them. Now curtailing curtailing the renewable resource is, of course, for control purposes a good idea and good to have, but in terms of maximizing the output, you would assume that you're putting in renewable power because it's competitive with the cost of generating with diesel. So if that's actually the case, then you wouldn't want to necessarily curtail it, but you want to use that power. So we ignored the case where you curtail it because that's actually fairly straightforward and easy to just shut it off. But went straight to working with managed loads. And now if you have a managed load, just like we heard in the previous talk, they're using boilers to dispatch additional hydro resources when they're available. You can do the same with wind or solar. It's being done around the state. Now you have a choice. You can either use just a single large managed load that you can turn on or off. And this is, of course, not what's generally done, but it's in the trajectory of the theoretical model. Interesting to look at. When you do that, you can already see that you're able to significantly increase the renewable penetration. Now we're still at a generator size distribution where one generator is slightly smaller than the other, and we're nearly able from the previous approach to double the theoretically maximum renewable penetration. Go on. Now if we if we go on and instead of having one single large load that we can turn on and off, but several small loads or a variable variable managed load, then we can further increase. increase the renewable penetration, and at that point, actually, the sky's the limit. You can, if with small enough load steps, you could use all the kilowatt hours that are available from a renewable resource. However, to do that, you might need a fairly large variable managed load, and there, of course, the cost then might just not warrant the effort to capture, say, the last 5% of renewable energy that would else just be dumped or diverted or curtailed. The interesting thing really is when you're looking at managed loads that the optimal size distribution for your diesel gensets changes. And that's something that we found really interesting because it also means that you have to plan ahead as to what you want to do in the future with your system. So to just not think it through from the end, as in this is where we want to go with the system when you start putting in renewable energy and managed loads, you really have to kind of look through what do we want to do, where do we want to be, and what can we do with what we already have, where can we actually go, because else you might find yourself in a spot that's just not optimal in terms of size distribution of engines. Of course, whenever you have a chance to change out an engine, you might want to revisit what that end goal was as well. So just to make it really clear, and this is all theoretical work, we have ignored essentially all the engineering challenges that many of you are dealing with every day. But it's a baseline for a framework that we're looking to develop that really tells you, you know, this is possible, potentially possible, versus this is impossible. So there's somewhere there is a line where that just based on the theory of things, you just can't go any further. And this is what you need to push your system to the next level. So as I already mentioned, the optimal sizing of diesel engines is actually variable with your control approach of your renewable resource and the auxiliary equipment you want to put in. Or vice versa, you might want to look at what you already have in your diesel plant and then make decisions about what you want to put on your grid in addition. And you do need a sophisticated control system to actually make your renewable system as valuable as possible. If you just add behind the meter renewable resources that you have no control over, then most likely what's going to happen is you have a problem because you're actually running larger diesels for less power output, meaning the cost, the fixed cost of running a plant is spread over less kilowatt hours, which raises the cost per kilowatt hour. Excuse me. 1 minute. Okay, I think I made that point already. So, thank you.
That either worked out perfect or he just quit in the middle. All right. Next up, we are going to have Jeremy Kasper, again from the Alaska Center for Energy and Power. He's going to be talking about ocean and river energy. He is the Alaska Hydrokinetic Energy Research Center Program Director and holds a PhD in oceanography from the University of Alaska Fairbanks and a BA in physics from Reed College. So Jeremy, come on up.
Thanks, Josh. Let's see. So I'm going to kind of give an overview of what AHRC is, what their role is in the state, and some of the projects that we've been working on in the last 3 years. This is a nice shot of the Tanana River in Newhalen, excuse me, that some of you might recognize. What you see here, this big V here, is actually a debris diversion technology for shedding debris that's coming down the river towards any turbine that would be installed behind there. So AHRC is really, our goal is to support statewide economic development. Emerging technologies such as hydrokinetic turbines, they're economically competitive in many places in Alaska because of the high cost of power. Alaska is therefore at the forefront of adopting these new energy technologies, as many of you know. Part of the reason for that is because it's difficult to transport fossil fuels and extract it, but there's also a lot of state support here, which is making the industry pretty viable. The knowledge gained here is also exportable to other developing countries as well. There are a lot of similarities between Alaska and Africa, a lot of South American countries as well. So the knowledge that we can gain here working on these technologies is really something that could be applied elsewhere as well. So Hertz Approach is to basically systematically identify challenges to adaptation of hydrokinetic technologies. One of our big focuses thus far has been on debris. As many of you know, if you go out on any river in Alaska, pretty much you're going to run into trees or log islands or even you know, who knows what. But that's one of the main problems that we've been working on so far. Then to approach that problem or to try and come up with a solution, we form industry partnerships and then assemble a team to address those challenges. As Josh mentioned, my background is in oceanography, not necessarily a straightforward connection between that and energy, but here I am. Jerry Johnson, who's my predecessor here at AHERC, is a geophysicist. We work closely with all of our research engineers. We work with fisheries biologists as well. And then Anthony Scott, who's an economist in Anchorage with ACEP, and we work with Marc, and then computer scientists as well. So a pretty broad team of people that work on these issues. So once we've identified the problem, we kind of identify and test solutions to problems. And then we want to really get that information out into communities. So basically come to Rural Energy Conference and other appropriate venues and basically let people know what things are working, what's not working, what looks like a viable technology. And then knowledge gained is enabling during that the knowledge we gain during that process is enabling. And as I mentioned, one of our research focuses thus far has been on debris. This is that debris diverter that I showed you previously. It's basically a V that sits out in the river. This version here, the angle is adjustable just because we wanted to figure out if there was an optimal angle for shedding the debris or reduce the friction versus a wider spread, those kind of things. Not necessarily what you would employ in a village situation, not the variable angle anyway. We also have this rotating cylinder on the front which helps shed debris. On the right there you see there's actually flappers that turned the cylinder. Those turned out not to work so well, so we covered them up with plastic. You can see that down there in the lower one there. We try to basically a straight on V, which didn't work very well either. So make mistakes and learn from them. So what we've been up to this summer has actually been building out our test site. We started with the barge that was in Eagle that was deployed as part of their Denali Commission AEA funded project to deploy a 25 kW turbine out there. That project ended and we ended up with the barge from it, and so we converted it beginning in about January to accommodate our testing needs. So here it is in about, what was it up top there? It was about June or so, and that's out at John's Machine Shop in Fox. And then down just about a week ago, here it is with Oceana Energy's turbine on it. So we were able to get it out and deployed. Got a hydraulic unit on there and even a weather port to cover up the computers, and it's quite functional in there. You can see it's behind our debris diverter as well. And then we were also building out our site in Iliamna. So basically in June of this year we started with nothing, ended up with some almost hospitable office conditions, but so we've been quite busy. But we now feel like our test site is pretty viable for developers to come up and test their technology in Alaska. And I should mention this is I think this is the only river test site in the world for these devices. So we're pretty excited that we've got it to this point. So Oceana, as I mentioned, was here for a couple weeks. They just finished up. Yesterday was my first day back in the office in about maybe a month and a half. So we're assisting Oceana with their deployment. We'll be testing our turbine there next summer. We have some questions we want to answer about how our debris diverter affects flow behind it, basically to see if it decreases flow or if it has a negative impact on energy production. We're also involved with other projects around the state. We're conducting the Yakutat Wave Energy Resource Assessment. We've got instruments out there now measuring the wave resource. This here is a nice plot of the wave energy from September through December of last year. You see, it's kind of hard to see the scale, but basically this is the wave height through time at Yakutat off of Cannon Beach there. In the summer and late September, you get pretty small waves. They're about 2 meters or 6 feet down to maybe about 3 feet, and then progressively bigger throughout the year. And you'll actually see at the end of the record there in December, we saw some 15-meter waves, so about 45 feet. And those are about that was about 120 feet of water, so pretty significant wave resource there. Unfortunately, our instrument stopped recording about a month after that, maybe because the waves were too big, but we're going to get it back out there again this winter. So just to summarize, AHRQ's a research, technology, development, and information resource for marine and river energies for the state and local industries and industry as well. We've got ongoing work on developing cost-effective resource assessment standards and techniques, working a lot on debris mitigation, looking at fisheries interactions with these turbines as well, and also the economics of them. And we're basically trying to enable a burgeoning hydrokinetic energy industry in the state so that we can push this energy source for the state, but also export the knowledge that we're gaining here to other places as well, and fostering a knowledge-based economy in Alaska, basically. So a lot of people have contributed to this work. Oceana is here in the room, and I'll divert any Oceana questions to Ned over there. Resolute Marine Energy is working in Yakutat, and then there's also a very large host of other organizations that have contributed to this. With that, good.
So last up, we're going to have Randy Hart talk about renewable energy integration and a hybrid approach. Let me pull up his bio here. So Randy is the hybrid project specialist at Planetary Power, facilitating sales and business development for North America. He studied aerospace engineering and renewable energy. He brings an innovative perspective to solving problems for off-grid power. And we're actually a little ahead of schedule, so I think Randy had a couple extra slides he was going to try and include at the end. So please, Randy.
Yeah, thank you. I really appreciate being here. Alan's not in the room, but Alan Fetters was integral in getting me and my company up here and promoting some of our technology and what we're doing with variable speed drives and energy integration so that we can have a higher penetration of renewables. Planetary Power has been around for about 7 years. We've been developing a couple of different technologies, and out of those technologies has been our diesel-electric hybrid system, which I'll kind of go into a little bit at the end. But first off, I just kind of wanted to give you a little bit of depth into the company and some of the things that we've been doing. Last year, we were working with the University of Hawaii and NASA on a Mars demonstration project. We took one of our hybrid diesel-electric generators with some photovoltaics up to the top of Mauna Loa in Hawaii. And over their conventional generator, these are just a couple of stats of what we're able to do for them over a 6-month time period. The engine runtime on this over 6 months was only about 900 hours on the diesel engine itself, while providing prime power 24/7 over the course of that time. The only failure we encountered was actually some photovoltaic panels getting burnt up, as they were putting out about 120% of the rated output due to the very low atmosphere and high altitude. So some of the energy must-haves that we try and make sure that we address every time is safety, security, reliability, and operating expenditures. And in those, we can really drive some good product development and integration, and I feel that we address a lot of the concerns that are found in rural Alaska. We're working well beyond rural Alaska in a lot of different industries and communities. I really like working up here in Alaska because you speak English, you use our same currency and our same code of laws. That might sound really simple, but compared to doing business in North Africa or Haiti or even the Middle East, it can get quite challenging for some of those reasons, regardless of all the other aspects of trying to integrate different energy sources. So in providing power on the frontier, like we like to call it, we find that a lot of the world faces these same challenges of providing steady, stable power. Of the population base, only a small percentage has grid power. And there's a very large amount that has no access to a grid, or their power grid is only good for 6 to 8 hours a day. And to try and do commerce or industrial activities when you don't know when the power grid is going to be available creates a very large economical challenge. Then the other thing that we find is that there's a lot of renewables that have become commoditized and are very cheap out there, but they're not sufficiently developed to meet all the needs of the people who are involved in acquiring power from those load sources. And just like rural Alaska, diesel generators are the key. Right now, that's been the workhorse around the world. Even the state of Hawaii operates almost solely off of diesel generators. They've gotten a lot of solar penetration and wind over the last couple of years, but up until then, they were almost 100% diesel. And then, like I said earlier, not having consistent clean energy really strangles businesses. And then further down the line, you have problems with heating and cooling and fresh water, and really have a large social impact that can limit a community. We're working with some folks over in Ethiopia, and I didn't know that the coastal communities have no issues with famine or disease. Because they have a very good fishing infrastructure. But you drive an hour inland and there is famine and disease everywhere. It's rampant. And you say, well, how can you have such good coastal resources so close to these other villages and towns that are having a lot of problems? And the simple fact is, the fish goes bad by the time they get it there. They don't have any resources to dry out or chill that fish, store it for the transportation inland. And so, even in those close proximity communities, having an energy deficit makes a really large impact. So we found that hybrid generation solutions can really provide a good bridge in between conventional technologies and pure renewable systems. So then we come to, there's been a lot of talk, this conference and many others around the world right now. Why hybrid systems? Why now? Not only has photovoltaics come to the point of a commoditized item that's become very cheap. We're seeing installed costs maintained around $4 an installed watt, which is excellent. But also we've had breakthroughs in battery technology, inverter technology, and a hybrid system can leverage those renewable systems so that you don't have to oversize your photovoltaic array or with a battery system that's very large if that's your only source of generation. And then we've got ever-increasing energy needs and costs. And so how do we balance not only our generation but our fuel consumption with that? Then the economic growth in these emerging markets without reliable power grids just won't happen. The more power that we pump into rural communities, the better chance they have of being economically stable and sustaining themselves outside of their own area. So the incumbent generator manufacturers have spent the last 15 years of their R&D on meeting EPA regulations and emissions. And they still don't have it right yet. They'll tell you that flat out. They know that they're facing challenges. Meeting these Tier 4 final requirements for the U.S. Has been a very large challenge for them, and it will continue to be. Here in Alaska, you've faced head-on many of the issues with the Tier 3 and Tier 4 engines, and that's not a near-term solution. They're going to continue to work on that, but many times that flies in the face of efficiency. That's not the driver for them. The government and the regulations are pushing them to be in, and it's just certain categories like we found, whether it's particulates or CO2, other emissions, and so they're doing what they can to change their systems to just get those right results. And anything outside of that realm almost means nothing to them at this point. And so we can find that they haven't spent any time on how they could better integrate with renewables or other power sources. So I kind of have a simple efficiency curve here. It might be a little bit extreme, but I kind of did that to illustrate what the difference is when you have a hybrid system versus a diesel generator. A diesel generator, the efficiency drops off quite a bit, where a hybrid system can be just as efficient charging my iPhone as it can be supplying its rated load. And we do that through energy storage. I'll talk about that in a little bit. But you have to size it to your peak load. If that's your only source of power and that goes down, that's why you've got to have multiple generators, because it doesn't have any inherent backups. And you constantly need refueling, continuous emission and noise problems, and then, of course, frequent maintenance cycles when you're depending on those for your prime power. So some of the things that hybrid systems do in conjunction with diesel engines is they're able to battle that new technology with technology. A hybrid system requires a control system, and that control system can better interface with the new interfaces of the Tier 4 final systems. Then hybrid systems can run combustion engines much more efficiently. Like Marc was alluding to, when you balance your load better, you get better efficiencies on your diesel generation. And then in a hybrid situation, you can even go diesel off. And there's no better fuel efficiency than going to zero fuel consumption. And many times that's our goal, to go with diesel off 50 to 75% of the time. The wet stacking and other problematic low load scenarios can be virtually eliminated in a hybrid system when running the diesels at their maximum efficiency. And we need to continue to develop these systems because the EPA regulations and other issues aren't going away. We've seen a lot of complexities over the last 10 years, and from what I've learned, it's just going to get more complex. Hopefully that we can, like I said at first, we can have that technology, battle other technology, and keep those things in check, but it's going to take a lot of effort to get to that point. So as you guys know, with distributed power, there's a lot of different costs to that. And I've got a small excerpt there from just off-grid telecom towers. Those are generally about 4 to 20 kilowatts, but they're a really good case study for, and I think a way that's going to push the hybrid market in the direction of reducing total energy costs, because they face a lot of the same challenges that you do here in rural Alaska. You have many remote communication towers here as well, and all of those have a very high cost of energy because of the soft costs, not necessarily the direct fuel cost, but getting the fuel there, the maintenance, the fuel logistics, and then if you've got a diesel-only system, the increased environmental impacts. So we found that energy storage is what really makes the difference with those. And here's just kind of a quick little pictogram of the way that we run a hybrid system, where diesel is still the baseline and can provide a majority of the power. And then here's my little symbol for wind, if you will. But we run diesel through a combustion engine, put that into a battery bank, and then can also utilize wind generation generation and photovoltaic generation into that energy storage. And then from there, we can get very clean power through an inverter and control system out to your home. It's very manageable, and we can size the renewable generation systems much higher to have a much better impact. This is a fun little graph I like. It gives you an idea what happens at the switchover point inside a hybrid system at the moment of going from diesel off to battery only. We've got a lot of different things going on here, but this kind of illustrates some of the complexities that you have to be managing inside that control system for a diesel system. So we've got a high voltage DC discharging out of our batteries. We've got our 3 phases of our inverter, of our output. Then we also have our output power to the load in kilowatt hours. And then the voltage of the batteries. And as you can see here, the battery voltage going up and down as the high voltage system is discharging. There's an inverse crossover of those as the voltage is being pulled from different sources. So then we can also have much cleaner power with a hybrid system. In the way that we utilize that, we provide power via an inverter. So we don't have nearly the issue of power quality that many other systems do. This is a single phase 2-wire system at 50 Hertz that we did for an Australian customer. Then this is putting a 12208 volt 3-phase 4-wire system at 60 Hertz together, and then more conventionally what you'll see here, your 120 240 volt 3-phase or 2-phase 3-wire system at 60 Hertz. These are just some of the output characteristics that we can have via our inverters. We can provide single and 3-phase power at the same time, and also within one cycle of this sine wave match another signal. So these systems play very well with others. So not only can we integrate renewables at the highest penetration, but we can connect our hybrid systems to any other energy sources and match that signal within 1 Hertz, essentially. So it's a little bit hard to see right here. This inverter is stepping, but it's stepping very quick. This is one of the more pure sine waves that you'll see instead of just a big block system that's going from a modified sine wave. So we're fairly happy with that technology. It's kind of a sexy looking sine wave for some of us geeks. But so now a little bit about energy storage. It's been coming a long way. In some of the other conferences that I've been to, anywhere from 1/2 or 1/4 to 1/2 of the speakers are based off of energy storage companies. These are just a couple of them that we've started to work with. Battery technology has come a long way. You've got a battery in your pocket right now with your cell phone. That cell phone would not be available technology without compact high-density energy storage, and we use some of the same technologies. Then the other part of this is battery management technology is key. Batteries used to be very dumb systems, flooded lead-acid batteries that we use with photovoltaics and the old systems, but we can't really use those anymore if we want to get higher efficiencies. So we've got to manage those battery systems, and each one of these companies have different battery management techniques, whether it be depth of discharge or the cycle rate. So just to give you an idea, Firefly Oasis has some new microcell lead acid systems. Beckett batteries using a Boston Power lithium ion cell, that's actually the LINMC chemistry. UET Energy Technologies is a new flow battery that's on the grid in Washington right now, working very well using a vanadium redox flow system. And then ultracapacitors are coming down in cost as well and can really help out with some peak shaving. So just real quick, I'll talk a few seconds about Planetary Power products. Our hybrid diesel electric generator, HyGen, as we call it, like I said, uses a conventional diesel engine. We can integrate renewable integration directly to a DC voltage bus. We've got a control system that manages every aspect of that, along with lithium-ion batteries in our mobile version. We use lead acid on a fixed site, and then full remote monitoring, connectivity, and control. And so the concept of this real quick, during a very low load, the engine is spinning, as you can see here, and it's providing power to charge the batteries and to the load. But as soon as the batteries are full, then it's providing power to the load by itself. But in the case of a surge load, or when the battery bank is depleted, we can spool up the engine and pull from the batteries for a greater output than the engine itself. Some of the specs, you can pick up a spec sheet from me outside. And this is just some of the efficiency gains that we see of a hybrid system over a similar size diesel genset. I mean, 40%, 30-40% is really common. In a lot of cases, we've seen as much as 70 to 80% just by incorporating energy storage. And so a cost breakdown on this, a lot of folks we deal with are really concerned with the capital costs, so we bring that on a monthly or lease basis. And what we see is a cost of generation, sorry, I didn't come through, but at about $4.40 a gallon, we're seeing on some of those conventional dumb generators as much as $1.09 per kilowatt hour in a variable load situation, where we can be very fixed at 39 cents per kilowatt hour with a levelized cost of energy at 58 cents per kilowatt hour. I've got some numbers on things we've been able to do in the telecom industry. I think the bottom line is the most interesting. Over 5 years, we're saving about $170,000, $180,000 in fuel costs for those systems. Not just in fuel costs, but reducing the amount of fuel trips, the amount of maintenance cycles, and then increasing the full generator life cycle by not having to run that diesel engine nearly as much. Then just real quick, I know we're coming to an end here, but our SunSpark solar thermal system is coming out of final prototyping, and we expect to have some results published next year, where we use the sun's energy, not just the photons, but the full spectrum of heat. We superheat ambient air and use that pressure to drive a series of turbines to produce power. Those turbines spin about 200,000 RPMs to produce about 10 kilowatts. So we've got much better energy efficiencies out of that system, and we can still be modular and mobile. So thank you all for having us here, and look forward to coming again next year.
So we actually finished pretty quick there, so we're going to have plenty of time for questions and answer. I'll walk around out in the audience with the microphone for questions. And before I do that, though, please remember to fill out an evaluation form for the conference. I know everybody wants to get out of here, but we really appreciate it when you can fill those out. So if you have any questions, I'll be walking around the audience. If you can walk up to the lectern. Test.
I had a question for Marc related to spinning storage, and you know, how sensitive is that to, you know, kind of shifts in foundations, things like that, like if, you know, or just being on a level surface. Or...
Oh, the flywheel?
Yeah, the flywheel.
It has to be quite level. So, I mean, what we did in the laboratory, we actually reinforced the floor with an additional 10-inch slab of concrete, which was leveled to, I think, 1,000th of an inch over 10 feet. So, yeah, you want to be level. We actually we had a hazard assessment this morning, and the biggest question everybody had was, what if we have an earthquake? Pretty much, if you hear a noise out of that flywheel, you want to leave. So.
Anybody else? Okay.
So on the hybrid system, if you have like a different variation of the PV for the depth of discharge on the batteries, so it's moving around a lot because you turned the diesel off, have you done any studies to see like how much less life you get out of the battery from doing like a 10% versus a 50% depth of discharge on the lithium-ion batteries that you have in your system?
Oh, yeah, definitely. The depth of discharge is directly related to the life cycle of the battery and the amount of charging cycles you can get out of that. Lithium-ion batteries have the capability of going very low in their depth of discharge, up to 80–90%. And in that, you can get probably 2,000 to 3,000 charging cycles. In our systems, we're only going to 50% depth of discharge on lithium-ion technology, but we're getting greater than 7,000 charging cycles out of those systems. So in a situation where we're going to that full 50% depth of discharge once a day, I mean, that's the better part of 10 years in life cycle for those batteries. And we've also gone with some smaller batteries that are very modular, and so in the case of a failure on one of those batteries, we can quickly replace those with another one and keep that engine uptime.
Hi, question for Marc. You showed essentially using two different diesel generators of two different size, but you didn't show efficiency curves for either. Does your results depend on the underlying efficiency curves of those generators?
Of course it would, yes. And yeah, there is of course a size dependency of the efficiency of diesel engines. What we found though, the sizing itself was not done based on efficiency of the engines in this particular optimization code, but just on maximizing a renewable penetration. And it turns out that you end up with engine sizes that are comparable to each other still. So I wouldn't expect that unless you have very different types of engines in your system. With these kind of size differences, you run at very similar efficiencies for those two engines that we have in our model.
Marc, while you're up there, I have a question for you. In your baseline scenario, you said that 70% average penetration was kind of the maximum you could get.
Right.
How much excess electricity are you dealing with in your system at that penetration level?
Okay, that would depend on your actual load profile. Now remember, this is a theoretical study that doesn't actually rely on load profiles, but just relies on respecting the operational envelope of the diesel plant. So it would really depend on what kind of variation you have in your system and how that relates to your renewable energy resource as well. So particularly with solar, you have just your diurnal variation and you're stuck with it. With wind, it's a little bit more random than that. This study only tells you what's possible at best. Okay, what's possible in reality is less than that. That's essentially the laws of physics.
Does anybody else?
Test.
If not, I have a question for. Oh, sorry.
I had a question for
On the
Marc,
hydrokinetics
related to spinning storage, and how sensitive is
you
that?
have the debris diversion. Is that floating debris, or you? Does that shade the shadow the energy producer from energy in the stream?
Yeah, the flywheel.
Well, so far we're just dealing with the surface debris problem. Subsurface debris is potentially a harder issue to deal with because, first of all, we're not working a system where we can actually look at it because you put your turbine in you lose sight of it about 6 inches below the surface, maybe a foot on a good day. So we are trying to figure out actually how much stuff is down below. The debris diverter that I showed is just dealing with the surface stuff. It only penetrates about that's about 2.5 feet below the water line there. One of the very last things that we did before we pulled the Oceana turbine is make some measurements at different distances behind that debris diverter to figure out that exact question, whether we're basically shading the power output from the generator from the debris diverter. So we don't have an answer to that. We did that on Monday, and like I said, we got back from the field on Tuesday.
So if nobody else has a question right now, I'll ask George. You talked a lot about the difficulties that you saw with your Run-A-River hydro. Can you maybe talk about the benefits to the community and you know, how many gallons of diesel? I know it's a lot of. How do you compare it to a diesel system?
We save about 200,000 gallons of fuel a year. Excuse me. When I started working for INN in 2009, they were burning between 30 and 40,000 gallons a year of diesel fuel supplementing hydro. Last year we burnt just less than 5,000 gallons. So the benefit is we're not burning diesel fuel, for one, and we have a very flat electricity cost. We have not raised rates with the price of diesel going up. Our electricity costs have been flat for the last 15 years. They've stayed the same. They haven't gone down, but they haven't gone up.
And maybe a follow-up of what's the difference in personnel that are employed from now versus when you were on diesel? Is it about the same, or are there more people employed? I know you said you had a lot of people that have to go out, break ice, that kind of thing.
Well, I hire part-time. When I started working there was basically one other person employed. Since then, I've hired another plant operator. The guy that was there retired. I've hired Terry there as the financial manager. I have a secretary. We've built a new office. We moved our operation, our financial operation and management out of Naknek Electric up to Newhalen. So I have one plant operator and myself, and when we run into things like you saw there, I just put out the word and start hiring young guys. 20-year-old guys are great. You point them at a block of ice and say, move that, and they do. Especially if you buy them lunch.
Well, we're finishing up a little early, but please thank our panel. And again, evaluation forms are up here. Have a safe flight home if you're leaving.